Juan start his lectures on machine learning and quantum matter.
All right, thank you. Thank you so much to Pedro and Nathan for the invitation. It's always a pleasure to be here. So I'm going to tell you about machine learning and quantum matter. You can ask me any questions, you can interrupt and ask whatever you want, like it doesn't matter. So I'm going to introduce the whole thing in the context of many-body physics. So the idea is we'd like to study many-body systems, and that the generic specification of a quantum state, such as the one Nathan was describing, the wave function, requires exponentially an amount of exponential resources that grows exponentially with the number of degrees of freedom in the system n. So for instance, if you have a system with a bunch of spin 1/2 degrees of freedom, then the wave function, which contains all the information you can possibly ask about the quantum state, is a vector with 2 to the n components, okay? So that's that grows very fast, and it is such bad that even with today's best supercomputers, we can only solve the wave equation, the Schrodinger equation, exactly for systems up to 45 spins if you use all sorts of symmetries and tricks. Yet, technologically relevant problems in chemistry and condensed matter and quantum computing are much larger than 45 spins. In fact, we want to take the thermodynamic limit, that is the limit in which the number of degrees of freedom grows to infinity or to a number of the order of the Avogadro number, okay? And so we can't solve those problems exactly, so we have to do something about it. Okay. Let's see. Yeah, so, but there's still hope for classical algorithms to handle this problem, okay? Because as some people say, nature is sometimes compassionate in the sense that the amount of information encoded in this quantum state is typically smaller than this maximum capacity, this exponential complexity, okay? And so nature has some structure that we can exploit to try and tackle those problems, okay? And so this is what techniques such as quantum Monte Carlo and tensor networks do. They exploit the inherent structure these problems have, okay? And so, for instance, when you do a Monte Carlo simulation or a quantum Monte Carlo simulation, what we do is a stochastic exploration of this enormous state space. And so you basically, what you do is you sample this space and you visit the most important regions so that you can compute observables and quantities that allow us to characterize the physics of the systems with little computational resources, okay? In tensor networks, what people do is they exploit the fact that quantum states, or many quantum states that are realized in nature, have little entanglement, and so you can basically take a generic wave function and split it in pieces in a way that allows you to perform computations on the systems, okay? So, so both techniques have led to profound implications to our understanding of condensed matter systems and in general quantum many-body systems, okay? So let me go ahead. So then we enter machine learning. So that's what I'm going to be talking about, right? Like, so the machine learning community deals with equally highly structured problems arising in data sets in nature, okay? And the insight that people have and that we've had for the past few years is that both problems in quantum many-body physics and machine learning have a lot of shared structure and symmetry, okay? So, so then the question is, what are these commonalities and are they important beyond just mere resemblance, and can we exploit them, and can we use machine learning in quantum physics? That's the idea, that's the question that we've been exploring for a while. So, and here is a representation of, say, the entire Hilbert space. You have physical states and then random states which are not produced in nature. And the idea is that there's a family of states that we can access with quantum Monte Carlo, with tensor networks, and then now with, say, machine learning techniques such as neural networks and so on. And there's some intersection between them, and so that's what we'd like to explore. So the first commonality is high dimensionality. So you imagine you have a camera, and this camera is very simple. It's how many different pictures can a camera take? That's one question we ask, and this is inspired by this computer vision techniques when you analyze, say, images or pictures of cats and so on. And so you can see a very simple camera with L by L pixels. So this camera can take only binary images. So each pixel can be either 1 or 0, for instance. And so this is one typical image. So each pixel can be 1 or 0. And so the question is, how many different pictures can this camera take? Okay. And first pixel can be 1 or 0, so that's two values. When you combine it with the second, the second pixel can be 1 or 0, and so that you can combine the two, and you get, say, 4 options: 0, 0, 1, 0, 0, 1, and 1, 1. Okay, so that's a camera with 2 pixels. Now, if we add a third pixel, you get even more combinations: 0, 0, 0, 0, 1, 0, 1, 0, all the way to 1, 1, 1. So that's 8, 2 to the 3. Okay. Now, if you take 4, you see what's going on, right? Like you get 2 to the 4 combinations, 0, 0, 0, all the way through 1, 1, 1, 1, and that's 2 to the 4. And then for L by L pixels, you can get 2 to the L by L. Okay, so that's that same exponential growth we saw in the problem of many body state. And so the space of all possible images is exponentially big, same as a quantum state. With spin 1/2 degrees of freedom, okay? Or the Boltzmann distribution in statistical mechanics, the probability distribution on such high-dimensional space, okay? Okay, so we have this, for instance, 28 by 28 binary images. That's a size of space of 2 to the 28 by 28, which is just big numbers. So it's bigger than the number of atoms in the universe and so on, and that's what people often say. But so there's no hope we can ever study distributions over such complicated state we would initially imagine, but luckily the probability distribution over images our brain understands is way lower dimensional than this generic 2 to the 28 by 28 probability distributions, okay? And the idea is that there's a low dimensional subspace in this enormous state space where images that we understand, or the brain understands, lives, right? Like, so we imagine this high dimensional space is 3D, and most of this space is filled with images that are noisy, that have low probability of appearing in a camera that we use to take pictures, okay? And so, and the cartoon is that these images live in a lower dimensional subspace. So here we're in 3D, and then the lower dimensional space is this line here, where those images that we understand live. And that's what happens in nature for quantum states. So the random states are, say, there's noisy images, if you want, and then the physical states usually live in a lower dimensional space. And so that's one commonality, again, with machine learning. So this commonality in the mathematical objects that we study. So for instance, in unsupervised learning, researchers are interested in understanding underlying probability distributions of a data set. So for instance, images of handwritten digits that look like this, and people want to know what's the probability of someone writing an 8 that looks like this, which may be assigned low probability because it's pretty poorly written, whereas this one, which is nicely written, may be assigned higher probability. So we're interested in understanding probability distributions over the high dimensional spaces, okay? So, and the way we can see a connection is when we study, for instance, the Boltzmann distribution of an Ising model, for instance, which is this energy function here, and the associated Boltzmann distribution, which is probability of a configuration with such energy is given by this Boltzmann distribution that you see, you've probably seen in statistical mechanics. And so when we study an Ising Hamiltonian, we use such systems. It's just variables or spins interacting on a, say, square lattice, and you get this interaction, and you compute the probability of such configurations, which very much look like probability of understanding, say, this image of an 8. Okay, so there's that commonality, and then when you study the quantum system on, say, spin 1/2 degrees of freedom, you write the wave function in a computational basis that looks exactly something like that, right? The wave function that Nathan was describing at the beginning of his lecture. Okay, so there's this commonalities, right? Like we're interested in similar high-dimensional distributions and wave functions. And then there's correlations and symmetries, which are strikingly similar. And so here, for instance, are critical correlations, and you've probably seen the Ising Hamiltonian in 2D. It goes at low temperature from a magnetically ordered state through a critical point where the correlations decay as a polynomial, the spin-spin correlations, and then at high temperature, it's just completely random spins. And then this beautiful example of someone took images from the woods in New Jersey, in a rural area, and they took thousands and thousands of images, and then they studied the distributions over the patches of the image, okay? And then they fitted Boltzmann distribution, and what they saw is that if you think of this distribution of having temperature 1, then if you vary the temperature of this image data set, then the specific heat of such system behaves as if those images were at a critical point, okay? Meaning that the correlations in these natural images behave the same way as the correlations in the Ising model in 2 dimensions, okay? So, meaning that there's critical correlations near the critical temperature of the data set are power law, the same as the Ising Hamiltonian in 2D. Okay, and these correlations are, like, these critical correlations are everywhere, right? Like in real data sets, they appear in music, in animal and flocks of animals, which is actually one important aspect that Giorgio Parisi, the Nobel Prize winner, studied a while ago. It's this. Is that all the systems have this commonality, right? Like these data sets that arise in nature, in natural language, in music, and so on. They all exceed the correlation or the power law correlations at classical or a quantum critical point. Okay, and strikingly also translational, rotational, reflection, and other symmetries that appear in physics often appear in machine learning data sets. For instance, you can imagine that a 0 is rotationally invariant, right? If you approximately rotationally invariant. If you wrote it perfectly, it is. But a number 8 is has a reflection symmetry, or 2 reflection symmetries. Number 1, if you write it perfectly, is also symmetric, and so all these commonalities appear, okay, in these data sets. Okay, so that's the motivation for why we think this is a good idea. But let me introduce learning. Okay, what is learning in the traditional computer science sense? So it's the activity or process of gaining knowledge or skills by studying, practicing, being taught, or experiencing something. So this is the dictionary definition. The computer science definition is a computer program is set to learn from experience E with respect to some task T, if and some performance measure P if its performance at the task measured by P improves with experience. Okay, so that's more precise. And so, what is machine learning? So, how can we solve a specific problem? Usually, so we can write a program that encodes a set of rules that are useful to solve the problem. However, in many cases, it's very hard to specify those rules, okay? For instance, some tasks in computer vision, in speech, in natural language processing are too complicated to establish, right? Like, so how do you define the rules to identify a number, right? Like in a picture. Or how you translate in natural language processing. It's hard to define these rules. So the systems need to adapt and handle noise. For instance, these images come with noise due to the fact that we write, we're tired, and sometimes we make mistakes, and so on and so forth. We often need to solve a differential equation, and we don't know how to do it, or there's no exact solution. And so in machine learning, where instead of explicitly writing a program to solve a problem based on rules, we typically use examples or training data to train a computer program or a computer to perform this task, and to generalize to examples that have not been used during your training, okay? And so that's the idea with machine learning. So learning systems that are not directly programmed to solve a problem, instead they develop their own program based on examples or data, or from trial and error experience trying to solve the problem, for instance, the way we do it in many, many cases. So this is different from the standard computer science approach to solving problems. We want to implement an unknown function, we only have access to samples of input-output pairs, which we call training examples, okay? And then learning simply means incorporating information from this training example into the system. So that's what we're gonna be doing. So for many problems, this is difficult to do by hand. So like, for instance, recognizing people and objects, understanding human speech, especially if you don't know the language. But the machine learning approach, what you do is you program an algorithm that automatically learns from data, okay? So why might you use a learning algorithm when you find that those rules are hard to code? Like, for instance, in vision, in speech, the system needs to adapt to a changing environment, like spam detection. When you get this spam email, this spam is always getting better and better. And so you need to adapt. And you want the system to perform, for instance, better than humans, okay? And other considerations. So here are a couple of examples. So from computer vision, so object detection, semantic segmentation, pose estimation. So these are examples in computer vision where segmentation is according to humans here. It's like they're segmenting different people, an animal, people, cars, and so on. And they're very useful for autonomous vehicles, medical imaging, precision agriculture, face recognition, robotics, all that stuff that you see on Facebook and on all the social media. There's also natural language processing, which is very, very interesting, very exciting at the moment. It's a branch of computer science, linguistics, and machine learning, giving computers the ability to process text and spoken words. It can be used in machine translation, which is when you go on Google and you do Google Translate, you're using natural language processing based on neural networks, speech recognition, sentiment analysis, automatic summarization of text, and more. It's very exciting. Maybe you've seen ChatGPT, which is this powerful algorithm which interacts with humans in a conversational way. So it has this dialogue format that makes it possible for the algorithm, ChatGPT, to answer follow-up questions, admit mistakes, challenge premises, and reject inappropriate requests. And it's all over the news, and you've seen it I bet you've seen it, but if not, you go and check it out. You can play with it. There's a free version, and it works really nice, really nicely. So people believe these models will have some deep technological, educational, societal implications, okay? So for instance, these models can pass the United States medical licensing exam and the bar exam for lawyers, so that's pretty crazy. As recently, so this is from February, I think a science fiction magazine closed submissions after being bombarded with stories written by ChatGPT. So it will have implications for writing papers, writing science fiction, and so on. And I asked it yesterday to write a poem about ICTP-SAIFR and the journeys into theoretical physics program. And so it's very impressive. So it knows a lot, right? Like in Sao Paulo, where knowledge blooms, a center of brilliance, ICTP-SAIFR looms. Within its walls, the curious minds convene, embarking on journeys into theoretical physics unseen. So it's pretty creative and pretty spot on, I guess, right? Because it knows what we're doing, and it writes decent poetry. Okay, you'll have access to the slides later. So, but yeah, like you'll read it. It's very nice. So it does all this sort of things, right? Writes beautiful text, helps you write your papers, improve your English, and more. There's one more example, or several more examples. So in using reinforcement learning, you can have these algorithms play games against, say, the professional players and win against. So right now, you cannot beat a computer at Go or at chess or and multiple games, all through reinforcement learning algorithms. Then in the sciences, there are more examples. There's this Alphafall, which is basically an accurate prediction of the three-dimensional protein structure out of the sequence of amino acids in the protein, which is a very hard problem, one of the hardest problems in biophysics and biology, and now considered nearly solved through machine learning. Okay, so that was it for motivation. Let me roughly categorize machine learning into two categories, and then I'm going to a little bit of details and in both categories. So one is data-based learning, which is the machine learning that we see in the news, right? Like in the mostly and the most important applications that we see out there. Okay, so we're provided with useful data that allows us to solve the problem. Okay, applies whenever it's possible to collect this data and to produce it and to do it efficiently. Okay, but there's also a broad category that's happening more and more in the scientific domains, which is learning models not based on data, but based on equations or laws of physics or chemistry, right? So instead of data, we're provided with an equation we need to solve, okay? And the examples are, people call them physics or chemistry-informed neural networks, and these are basically neural networks that can embed knowledge of any physical or chemical laws that govern the systems, okay? For instance, eigenvalue problems. You're given some matrix, and you are asked to compute the eigenvalues and eigenvectors, and that's all you're given. You're not given any data, and you can use machine learning techniques to try and approximate those solutions. Okay, so I'm going to focus on both. I'm going to have examples on data-based learning, but also equation or law-based learning. Okay. There's also combinations of the two. Sometimes you have a problem that is given to you in terms of an equation, and you may be able to find solutions to the equation in some regime, and that's your data. And then you can also encode the understanding you have about the differential equation or the equations of motion that you have, and you can combine this data and the physical law to come up with a solution in regimes where you can't find the solution, okay? Or sometimes you don't have solutions at all, but you have data coming out of an experiment. But you have a rough understanding of the experiment, and you can combine the data you collected from the experiment plus the expected behavior in terms of a physical law to come up with solutions as well. Okay, so I'm gonna start with data-driven learning. And I'm going to focus on first of all, on telling you about what's the different categories within data-driven learning. Okay, so the first one is supervised learning, where you have a data set of pairs X and Y, and you learn a mapping from X to Y. Okay, and examples of this are classification, in which, for instance, you're given an image and you're asked to say what's in the image. Okay, for instance, a cat or a dog, or a digit of 3 or 4, and so on. That's classification. So there's a categorical output, so that can be object recognition, classifying a phase of matter from measurements. And then there's regression, which is real valued output. For instance, when you're given a set of characteristics and you're asked to predict, I don't know, something, for instance, the market price of a house, given the number of rooms and the size of the house, okay? Or customer ratings and so on. Then there's, so this is supervised learning. Then there's unsupervised learning, which is given data points, find some structure in the data. For instance, you can imagine doing dimensionality reduction, which is going from this very high dimensional space to subspace where your data may be better explained. Like the image examples that I had this 3D noisy images, and then there was a line where the images live. So that's the finding this dimensionality where the data lives is called dimensionality reduction. The other example that we'll see in more detail is learning a probability distribution. So you're given data set and you're asked to estimate what's the probability distribution underlying the data set that you collected. And then there's a related problem in quantum mechanics, which is, or in quantum information, is called quantum state tomography. Quantum state tomography is when you go to the lab and you have an experiment, you measure the state, and you're asked to estimate the quantum state out of these measurements, or a quantum state consistent with the measurements that you collected in the experiment. Then there's other ones that I won't discuss. Online learning, which is a supervised learning technique when data is given sequentially by an adversary, no separate train or test phases. And the example is spam filtering, right? Like you keep sending emails, and these emails are adversarial, right? Like they're trying to fool you into believing that you should read those emails. And then there's reinforcement learning, where you learn through experience. You're an agent, and you go into a world or a world, and then you try and achieve some task, okay? And you repeat this on and on until you make it work. Like, for instance, flying drones automatically. There are other categories that I won't even talk about. Then there's machine learning in terms of equations and physical laws. For instance, we can be asked to compute the eigenvalues and eigenvectors of a matrix or a Hamiltonian. And so these are Hamiltonian-driven learning or matrix-driven learning. You're asked to approximate the dynamics of a classical or a quantum system, or you're asked to solve for the stochastic reaction dynamics in a, say, in a chemical reaction. So this is written in terms of a differential equation. You're asked to approximate the equilibrium properties of a system in thermal equilibrium, or approximate the steady state of an open quantum system, and so on. So for all these approaches, it is possible to reformulate the problem as a variational approach, and you can use machine learning techniques to try and solve this variational problem. Okay, so let me introduce the simplest algorithm, which is supervised learning. Okay, so in supervised learning, there's an input X, and you're typically think about it as a vector of features, and you're asked to predict some target T, and this is also called the response or the outcome or the output, and the objective is to learn a function F that predicts T as a function of X, and then F is a model that you construct, okay? And the idea is to learn this function or to infer this function, you're given some data set with n pairs X and T. Okay, so that's the setting for supervised learning. It can be a regression problem or a categorical problem, a classification problem, and I'm going to focus on categorical labels where T can be either +1 or -1 or 1, 0 or 1, 2, and 3, and so on and so forth. Okay. So classification is then, so given some d-dimensional input X, predict a discrete value target. And in this case, I'm going to take it binary. For simplicity, you predict 0 or 1, and the training examples are with t equals 1 are called positive examples, and training examples with t equals 0 are called negative examples. Okay, so you can also call them plus or minus 1. It doesn't matter. And then we build models y or f as a function of x, and y should match variable t associated with this data set with their data point x. Okay, so those models will have a set of adjustable parameters that we will tune such that our function predicts the data set as best as we can. Okay. And we'll introduce neural networks. So the algorithm that I'm going to explain quickly is based on neural networks. So what are neural networks? They're function approximators, and they're based on a basic unit. Okay, and this unit looks like this. So there's an output node that we'll call y, and there's some input that we'll call x. It's a vector x1, x2, and x3. And then there's a set of weights, W1, W2, W3, that will be the parameters of the neuron, okay? And basically, the most simple neuron, or the basic unit of this neural networks, looks like this, right? Like, so you have some input vector x, you multiply it by a matrix, or by a vector of weights, W1, W2, W3, and then you add some bias. So the vector W and the bias B comprise the parameters of the neuron, okay? And then you apply an activation function or a nonlinear function, and you do that on this linear transformation of the input, and that becomes your output. So graphically, this whole equation is represented in this way. So typically, phi is a nonlinear function. It can be between 0 and 1, kind of like mimicking the neuron, or a neuron in the brain where 0 is inactive and 1 is active. And by putting together lots of those incredibly simplistic neuron-like or neuron-inspired processing units, we can do really powerful computations, okay? So that's the idea. So this is the basic element. And so we can connect lots of these units together into a directed acyclic graph, so which is a graph that has this edges direction and has no loops, okay? And so here we have, so typically these units are grouped into layers. So for instance, here I have my input layer, which is just the input. And now we have a first hidden layer, which, if you want, is composed of a few of these basic units here, and then we compute this H1, H2, and H3, and that's the first hidden layer. And then these units here, become the input to the next hidden layer, the second hidden layer, and you compute them exactly the same way as I was explaining in the first basic unit, and you keep going on and on until you hit the output layer, which in this case has 2 outputs, okay? Each of these circles is a unit, yes? Yeah, so the question was, if on this process you have a learning process, right? Like in this computation. So far there's no learning process. I was just explaining how you do the computation of the output, okay? But the learning process I will explain in the next couple of slides, okay? Okay, so that's a so-called feed-forward neural network. Okay, it's just a composition of small computations that look like this. Okay, so each hidden layer ni-1 connects to, each hidden layer I connects n input units to n output units, right? Like, in a fully connected layer, all input units are connected to all output units, okay? So meaning that this is connected to each of the output units, so each of the inputs. Yes?
You said that typically you have that layer structure. You said that something like that in the last slide. Is there any case in modern research where you don't have a layer structure?
So the question is if there are architectures that do not have this layer structure, is that right? So there are other architectures that have some sort of recurring connections, for instance, right? But ultimately, the ones that I know have this feed-forward layer-by-layer structure. There may be other ones that I'm not aware, but the ones we're going to be looking at are all, they all have a similar structure. Okay, okay, the inputs and outputs for a layer are distinct from the inputs and outputs of the network, okay? So meaning that this is the input, but this other ones here may become the input to the next layer, okay? And then the outputs of the entire neural network are, sorry. Yeah, so I said this already. So phi is typically applied component-wise. So basically, when you say that this layer has some activation function, what it means is that you apply phi to this unit and then to this unit and so on and so forth, element-wise. So yeah, that architecture I just described is usually called a multi-layer perceptron. And there's some common activation functions. So this one is the identity when you have no nonlinearity. This one is called rectify linear unit, where it looks like this. So before, if the input is negative, you output 0, and then if your input is positive, you output the input. This is soft plus. Oops. This is a step function, a logistic function, hyperbolic tangent. You can use many different ones. So each layer computes a function so that the network overall computes a composition of functions, right? Like, so for instance, you have your input X and you compute this composition and you get those hidden layer, H1, H2, and H3. And then you apply again W2 times the input, which in this case it becomes H1, plus some second bias B2, and so on and so forth. Okay, so basically the output of the neural network or the feed-forward neural network is basically a composition of this type of functions, F1, F2, F3 on the input f of x. Okay, so that's how they work. It's just a bunch of functions that you apply sequentially, starting from the input x. Okay, so what's a neural network? It's just a complicated function that has parameters w that we can play with or tune so that they behave in a way we want it to behave. Okay, so that's that's a summary. Then there's the learning part and how we quantify it, right? So there's a loss function that defines how bad your function behaves with respect to a particular task you're interested in. Is there a question? No. Okay, so there's some example X and it has some label T. And so we would like to measure how bad is our function Y at predicting T from X, okay? And so we measured that through, for instance, a square loss function, which is basically Y, the output of the model, the output of the neural network minus T, the target. And if we square it, then that tells us how bad our neural network is behaving, okay? So if Y is very different from T, then this number is gonna be large, but if Y is equal to T, then it's a small number, okay? But it's just one example. There are many more loss functions, okay? So y minus t, people call it residual, and we want to make this small. This prefactor of 1/2 is for convenience when you're doing calculations and so on. And then so that's what we call a loss function, and the cost function is a loss function averaged over the training examples I was talking about earlier. We had a training set of n examples, and then so we average the loss function over all the examples we have, yi minus ty, and that's what quantifies the quality of your model, the quality of your neural net. And if you think about it a little bit, these are the predictions given by the model, and this model, remember, contains a bunch of parameters W1, W2, all the way through WL, and biases B1, B2, all the way through BL. And those are the parameters of our model, okay? And so this expression here will depend on all those weights and biases that I mentioned and that I summarize as bold small w, okay? So those are the parameters of the model. Now, so when we have not trained the model, so this may be very large, right? Because on average, if the model doesn't know anything about the data set, these predictions will be wrong, right? But what we want is that this object is small, right? And so we'll try to make it small, and that's called learning, right? And so how do we learn? We use what we do is we solve a minimization problem. Minimization of what? Minimization of this cost function j of as a function of the parameters w. Okay, and so recall from calculus that the minimum of smooth function, if it exists, occurs at a critical point. That is a point where the derivative is 0. Okay, and so there's a multivariate generalization, which is we set, or what we do is we set the partial derivatives of the objective function with respect to all the parameters in the model to 0. Okay, or equivalently, we can set the gradient to 0. So the gradient with respect to the parameters of the neural network is just this vector, and we set that to 0. Okay, so usually when we do this, there are two ways of doing it. One is a direct solution, where sometimes we can say directly find provably optimal parameters. So you set the equations of the gradient to 0, and then you do algebraic manipulations, and you solve for the parameters of your model. And that's it's called direct solution. That's very rare to find in physics and in machine learning. And we often cannot do it analytically. So, but there are iterative solution methods that repeatedly apply an update rule that gradually takes us closer and closer to the solution. And that's what we're going to be exploring. And this is what we're going to be applying. This applies to neural networks. So it's basically impossible to find these solutions by directly solving, and so we won't do that. So what we do is we do something called iterative solution by gradient descent. So all optimization problems we cover in these lectures do not have a direct solution, and so to minimize this cost function, we use a broadly applicable gradient descent technique, okay? And the idea is we initialize the weights to something reasonable, for instance, to zeros, and then we repeatedly adjust them in the direction of the steepest descent of the energy landscape, or this cost function landscape. So here I have an example with only one dimension where we have this, say, parabola, and we initialize our parameters here, and then we ask what is the direction of the steepest descent. And then we do a small step, and we come here. And then we come to W1. We ask again, what is the direction of the steepest descent? It tells us we should move in this direction, and we do it again. And this direction of the steepest descent is given by what? By the opposite of the derivative of the function with respect to the parameter w. That's the opposite of the gradient, okay? And eventually, if you repeat this on and your function is convex, you converge to a point near here where the derivative of the function is 0. Okay? So that's broadly applicable, and even in 2D or in high dimensions as well, and that's where we'll be using roughly. So if you observe like if the derivative is positive, then increasing W increases the function, okay? So let's say if you're here, the derivative is positive, and then if you increase W, then the function grows, okay? Whereas if you have a negative derivative, then increasing W, the parameter decreases the function, okay? So if you're here, the derivative is negative. If you move this way, the derivative, so the function decreases, okay? So that's the idea. And so this update rule always decreases the cost function if you have a small so-called learning rate, okay? So it's basically you change your parameter by W, whatever your W is, minus the small number times the derivative because of this observation. Okay, alpha is called learning rate or step size, and the larger it is, the faster your changes. Okay, so if the cost is a sum of n individual losses rather than their average, a small learning rate will be needed. Okay, so if you didn't include the average, if you didn't include the n, then you have to make this alpha, this learning rate, smaller. Okay. But it doesn't matter. So that's the idea with gradient descent. And this is the vector version of it. As basically, the example I gave was in one dimension. In higher dimensions, you basically transform these W's into a big vector of parameters, and you follow the same rule. And if it converges, then we get a critical point at which this derivative is 0, and so your parameters do not change anymore. Yes. So the question is if there are problems with local minimum, and the answer is yes. So that's the problem with gradient descent. So suppose the function looks like this, and then you start your parameter here. Okay, W 0. Then you will eventually apply gradient descent, and you will converge to this point, which is not optimal, okay? Because the optimum is here, W star. And so this is one of the problems, or the main problem this type of algorithms have, and there's no solution to this problem if you want. There's things you can do, which is initialize your architecture from different points or different initializations, and then try, and eventually you will find the minimum. But if you can imagine that this is one dimension, when you go to very high dimensional problems, this strategy will take you not too far, okay? But very often in practice, what happens is that the minima, the local minima that we find is often very good, okay? Yeah. So the question is if there are a number of iterations for you to know if you're reaching a good minimum. I don't think there's a good answer to that question. I think you just do a lot of trial and error. Mm-hmm. Yes? The correct alpha, you mean? So it's also by trial and error. It's by experience. Mm-hmm. You have to, so it depends a lot on the curvature of your optimization, but you don't know the curvature a priori when you set the problem at the beginning. So you do it, and so let me show you what can happen. Suppose this is your optimization, and then your learning rate is too high. Then what happens is you predict this direction, but your learning is high. Then you may come here to say, suppose this is W0, and this is W1, predicted by your high learning rate. You come here, your function was actually higher, right? And you compute again, and it tells you you should go this way, as it should, but your learning rate is high. So you actually come, say here, W2, which is even higher. And so one heuristic to set your learning rate is my cost function diverging? If it is, you should decrease it. Okay. The other one is when it is too small. If you're making very small steps or a very small reduction of your j, so what you usually do is you track j as a function of iteration time. If you're making little progress, then it means you should increase it, right? Like it should so that it looks like this. That's a good alpha, so too small. Okay, and too big, right? So you do it it's a heuristic, right? Like there's no simple way to do it. Okay. Let me go ahead. So that was it. So that's what we do, right? Like we have, first of all, a data set of pairs X and T. We have a model that is this function f of X that predicts Y that should become the same as T. And so we have a model and a data set, and then we have a learning algorithm that tunes the parameters of the model W such that this J is very small, okay? Such that our predictions match the data set or nearly match the data set, okay? There's more details, but let me just, as a first approach to the classification problem, these are the 3 or 4 basic ingredients, okay? So that's the first thing. Let me give you one quick example of how we used it a while ago. And so there's the easing model. At, say, a low temperature, we know that the spins align either down or up. And then as we increase temperature, the system starts having thermal fluctuations up until a certain temperature where the spins or the average magnetization becomes 0, okay? That's called the critical temperature. And then if you keep increasing the temperature, you get into a paramagnet where the spins are basically fluctuating and completely random, okay? So that's the behavior of the Ising Hamiltonian. So we have some sort of magnetization, which is the average over the spin values over the probability distribution given by the Boltzmann distribution. There's a critical point, and then the magnetization is 0, and basically the spins are random. Okay, so one of the first examples we did when I first started thinking about machine learning was, can we think of detecting or learning a phase transition as learning digits, right? Like, and so I thought maybe a 5 written can be understood as a perfect 5 plus fluctuations, given by how different people write different numbers. And so what I thought is, I mean, machine learning community has developed these neural networks, right, that can accurately classify an image of a digit and tell the computer that's a 5 or a 2 or a 0 very accurately, okay? And so I thought maybe machine learning algorithms can detect whether, obviously, this is all spins down versus completely random. Okay, so that was the first example we took a look at, and so what we did is we collected samples from Monte Carlo simulation of the easing model, which many of you may have done it before, at low temperature and high temperature, and we asked this algorithm, this artificial neural networks, to predict that comes likely from a low temperature simulation or from a high temperature simulation. Okay, so that was the first example we looked at, and these are the results. So these are the output of the average output of the neurons in our neural network. So this is the so-called cold neuron, the neuron predicting that these configurations come from a low temperature, and the red ones are the output of the neurons predicting that looks like a high temperature configuration. And what we saw is that they cross over near the critical point of the Ising Hamiltonian. So basically what it does, what this neural network does is basically learns how to distinguish these configurations. And it does so based on computing the magnetization of the spin configuration. Okay, so that's what we learned, right? That these neural nets use the same quantity that we typically use, basically the same order parameters. So this neural network initially doesn't know anything, but eventually gets trained to compute this object internally within the neural network, okay? Which was very nice at the time. We also learned that if you train on the square lattice, so this function, this neural network computes the magnetization. So you can expect it to, if you train it on the square lattice and you change the problem to the triangular lattice, you don't even have to change the architecture anymore or retrain it, because it learned something fundamental about the phase transition, so you can use it to predict the critical temperature of the triangular lattice, for instance. Okay, so training on the square lattice can help you predict the critical temperature of other systems, like for instance the Ising Hamiltonian on the triangular lattice. Okay, and you can compute critical exponents out of the output of the neural network and so on. So that was the first example I ever encountered or I ever studied about using machine learning. We also came up with a toy model. So a very simple architecture, only 3 neurons. And what we saw is that initially, if you predict, so this is the first neuron, right? Like the first neuron that we compute, this basic unit that we computed. Yes. So the question is, if you learn something fundamental, can you change the lattice? Well, the lattice, yes, and then can you change dimension? And the answer is yes, because if your order parameter remains the same, when you change dimensionality, then you will be able to detect it. There's some aspects that won't be captured, because some of these weights depend on the universality class of the phase transition, but overall, you will be able to detect the critical point. Yeah. So this is the model before training, these basic units before training as a function of the magnetization of the configuration. So initially it looks completely random, but as you train the model, it becomes linear functions of the magnetization, meaning that this neural network is actually internally computing the magnetization and using it to predict the phases, right? Like, or whether it comes from a low temperature or high temperature. Okay, and this, we came up with a model to do it, and we can solve for this epsilons. It's very simple, but it's basically that idea that this neural network learns the magnetization. Then eventually people explain the whole thing with renormalization group, and came up with solutions and models that explain the behavior of this machine learning algorithm. So that was nice. And that's it. So I think I'm done, right? Like, what time is, should I finish?
Yeah, now it's exactly 1 hour, yeah.
Okay, so let me finish with this example, or with the conclusion. So this neural network analysis enable us to make somewhat quantitative predictions about the critical points, and inform us about some universal properties like critical points and some critical exponents, not all of them, only from raw configurations obtained numerically and hopefully experimentally. So there are experiments that do this on quantum systems and so on. I just didn't have time to explain them. So we have made use of the knowledge of the critical point when we were training this neural networks, but this limitation has been lifted already. by a lot of people. So this was the first example of people not using the information about the critical point of the system, but actually discovering the critical point too. So they can discover critical points and critical exponents or some critical exponents. And so that's, yeah, and let me just conclude right here and maybe take questions if there's time. Yeah, there's one. At high dimensions. Mm-hmm. Graphically. Which solution? You mean the solution given by the neural network, or the solution of the problem in high dimensions?
If it's a long question, it's better to use the mic.
Thank you.
So if we have a 1, 2, or 3 problem, no, that 1, 2, or 3 dimensions, we have this problem, but it's more easy respond or found a solution in high dimensions, no. So how can we represent this solution in graphic form? It's possible or not possible?
I'm not sure I understand the question yet. So what do you mean by the solution? Is it what solution? The solution of the Hamiltonian or the neural network, or?
No, for example, we have a regression.
Regression, okay.
Yes. If we take this regression and put in other dimension, high dimension, it's more easy to see the curve. So, but we can represent this in graphic form.
You mean something like this?
Yes, but when we have n dimensions. So.
Yeah, so that's very difficult to visualize, and I don't think there is a. I mean, what you can do, what people often do, is they take cuts in the space of parameters, right? And then they take a few, and they plot this cuts along the different dimensions, and then that gives you an idea. But that's not perfect, because you will always miss some dimensions, right? Yeah, you can always find an approximate solution, even in high dimensions. The problem is visualizing. If the question is visualizing, I don't think the only thing you can do is to do cuts in the weight parameter space. Yeah.
We have time for more questions. Yeah, this is the.
You were speaking about using the neural network to analyze the critical temperature of ferromagnetic change into a paramagnetic, and that reminded me a lot of denoising, of you think of that about like slowly adding noise to a system until it becomes unrecognizable. Is there any research on that direction of using denoising neural networks to analyze physical systems?
I have not seen it, but sounds reasonable to me. Yeah, but I have not seen it.
Let's say if you look at that graph in just 2 dimensions, you can only take the steepest descent, but maybe for bigger dimensionality of the parameters, is there another techniques in the direction of the descent that are not the steepest descent that may allow us to not fall in local minimums?
Yes, there are other techniques that allow you to not get stuck in local minima, and that probably converge to this point. But often these techniques scale poorly on average, right? Like, for instance, you take a Monte Carlo simulation and in this parameter space, right? Like you make moves, Monte Carlo simulation moves, and you simulate the thermal state where your energy is your objective function J. So Monte Carlo simulations probably converge to a thermal state. So in particular, if you lower the temperature, eventually you'll be able to reach this point, but the convergence time to hit may become very, very large, okay?
So let's say the most usual way to do this is just to take the steepest descent.
Yeah, steepest descent is, if you wanna, you can think of it as if you're doing Monte Carlo simulation at 0 temperature, so you always go down. Yeah.
Okay.
But if you do that and with a very tiny temperature, if you wait very long time, eventually you will be able to hop here. But you will have to overcome this minimum, meaning that the Monte Carlo moves that will take you from here to here will have to climb this hill, and that becomes very unlikely, and the time will diverge with the size of the barriers that you encounter. So there are ways, and they probably converge, but in practice they're not useful because they may take a very, very long time.
Okay, thank you.
Mm-hmm. And there are more techniques, but yeah, that's one of them.
What supervision training can you use to on a solid three-dimensional?
So can you repeat the question?
What supervised training can you use to a three-dimensional solid?
Like three-dimensional easing, or which? So we can use the exact same.
When you see the change about from magnetic to paramagnetic, you use a solid bidimensional, I think. So what change if you use a cell unit of three-dimensional solid?
So I think nothing changes. So the interesting thing about, let me see if I can get there. So I guess the key thing here is there's no dimensionality of the input in this architecture. So this input neuron, so each spin in this 2D lattice becomes one circle like this. And they're connected all to all, okay? So there's really no dimensionality, or let me put it this way, we do not account for the dimensionality of the system when we use this particular architecture, okay? And then so if you do it in 2D or 1D or 3D, it will always get mapped to an input that's always a vector. So you don't have to change anything about the architecture if you're doing it in 3D. Okay.
Thank you.
So here, about the step function, the step that we take for minimize the weight. So if we have a higher derivative, can we lower the step or lower?
You mean this thing here, or?
No, sorry, it's the alpha. The alpha.
Alpha,
Alpha.
Sorry, yes.
Here, yeah, if we have a higher derivative, we can like lower the alpha or get a higher alpha for lower derivatives so we can get faster to the minimal point, or does it make sense?
So are you saying if we had information about higher order derivatives, can we use a higher alpha, or?
Yeah.
Is that the question?
Yeah.
Yeah, so there are many, so this is the simplest optimization technique. It uses only information about the first derivative, but using information about the curvature, for instance, can help you get better solutions with the same amount of computational resources, right? The problem is there has to be a balance, because computing second derivatives in a very high dimensional optimization problem, it becomes very expensive. You have to compute what people call a Hessian, right? And this, if you have many parameters, then this matrix is very large, and so it becomes very expensive to use. For instance, maybe you've heard of Newton's method. So Newton's method uses information about the curvature to get faster to the solution, but it becomes very expensive, and in practice, it's not worth it, at least for neural networks. So of course, there are problems for which it's worth it, and it could be used and it should be used, but for this type of architectures, that's not the case. Okay. And so people do not use them. They're too expensive.
And I want to make another question about the weight functions. Yeah. So for how we used the weight functions in that example that you gave about the Ising model for the magnetization, the active functions for the hiding layers. Sorry. Where did we use it?
I'm not sure I understand, but you're talking about
yeah,
here?
Yeah. I mean, the weight where the weight functions are used to find the magnetization at this point.
Yeah. So we have a neural network, right? Like, and this neural network predicts this output, right? Like, if you have a configuration drawn at low temperature, it will tell you this is drawn at low temperature with high probability. If it's drawn at high temperature, this one will tell you it's drawn with high probability at high temperature, right? So this is the output of the neural network, right? Like those two functions, right? Like the blue function and the red function. Now, how we read the magnetization was a little bit different, right? Let me explain you. So we had this unit, right? So X in this case is spin values, is up or down, up, down, etc. Right? And then we have the weights at the end of the training procedure, W1, W2, W3, and some bias B. Okay? And what we did is we computed this object, right, in the first layer of the neural network. So we computed this object W times X plus B. Okay? And then we plotted this expression here as a function of the magnetization, okay, which is this here, right? So before training, so when the parameters of the neural network do not know anything about the phase transition and about this data set, if you plot this, so look, this is those units, right? Like this W times X plus B. So as a function of the magnetization of the system, it looks completely random before training, okay? But then when you train the model, so this is what these units look like, right? Like as a function of the magnetization, they look perfect functions of the order parameter of the system, okay? So it's not that the neural network automatically tells you, I am reading the magnetization. It was through plotting this function that we discovered that that's what it was doing. Is that clear enough?
Yeah, thank you.
Thanks.
So can you use machine learning to distinguish phases that doesn't have an order parameter?
Yes, so I had an example, but I didn't have time to get there. But let me ask you, so can you distinguish these two? Right? One is a 0 temperature configuration, and the other one is infinite temperature. You can take a guess. Obviously, like, so this one is a ground state, and this is a high temperature state. So these are configurations, and the interesting thing is this one comes out of sampling the ground state of a model called Wegener's gauge theory, okay? It's a classical system in 2D that has, this Hamiltonian, right? Like Wegener's Ising gauge theory studied since the 70s, right? And it has a very interesting ground state. At 0 temperature, the ground state is a highly degenerate manifold with exponentially decaying spin-spin correlation functions, okay? And the ground state is said to be topologically ordered it's said to be a topologically ordered phase. So this is the Hamiltonian. It's a sum over the plaquettes of the square lattice. The spins live on the edges of the lattice, and this product over the spin variables up or down is a product over this four configurations. So the phase diagram of the theory is at t equal to 0, you have this ground, like this degenerate manifold, and at any finite temperature, you have the high temperature phase. And then we asked that question, right? Like, can you distinguish? And when we use this feed-forward neural network, it was difficult to apply. Okay, so it didn't work. It basically randomly guessing because it's hard to distinguish. But then we found a solution which was in terms of so-called convolutional neural network. Okay, and when we use this convolutional neural network, this convolutional neural network distinguishes with 100% accuracy whether you're seeing something like this or something like that. Okay, and what it does is it goes and checks every plaquette. And so the idea is, so the ground state is such that the products over each plaquette should be 1, so that you gain energy from this minus, okay? And so if you go and check that the product over each plaquette is -1, you know that this is a ground state, okay? And so that's what a neural network, convolutional neural network does. It goes and tests every single plaquette for products over the different spins. Okay, and for that we also, I mean, we did it numerically. We trained the model and it learned, but we also came up with simplified neural network architecture that performs this computation. Just check every plaquette whether you have this satisfied constraint of the product of the spins being 1. There's one question.
Yeah, there's one more question here.
Yeah, so I know the model you showed, it's just like a toy model. It just has like an input layer, a hidden layer, and then the output layer. But I was wondering what happens if you have like more hidden layers. I don't know if you tried it. Like, do you see like some kind of overfitting or something like that?
Yes, so I didn't talk about overfitting, but we didn't see overfitting. We had way too much data for you to see overfitting. Yeah, and when we tried deeper and more complicated architectures, we didn't see it because we could have a lot of data. And this is very simple, right? Like this gets trained to learn the magnetization very quickly, and so with that you always generalize. Yeah.
Is there any physical meaning of the loss function, for example, for the IC model?
We didn't come up with any physical...
Just computational.
Yeah.
Just, okay, thank you.
Well, if there are no more questions, let's thank Juan.
Thank you.